Hi guys, hope you had a really good Easter. Welcome back. It's me again, Sean. We're still in lockdown, which means that I still get to deliver lessons from home. Lovely piece of art behind me, bought by my wife at some point. Um, yeah, it's really heavy as well. I'm not quite entirely sure um, what it's doing to our wall, but that's okay. What we're going to talk about today is synthetic roots. And I'll just get my PowerPoint loaded on the screen so I can see it. But before we do that, what we're going to do is just sort of discuss a couple of bits and pieces. Firstly, well done for all of those of you who have submitted work so far. I know we're sort of moving between submitting it on Teams and Notebook. My preference personally is to have the work submitted as an assignment on Teams, because then I can sort of get it, mark it, get it back to you, or just check that you've done it. I know that Nick and Judith at the moment are preferring work to come through on the Notebook on Microsoft. I've totally forgotten the name of the program, but the open notebook or whatever it is. So as you've been instructed by your teacher, if you just make sure you get the work in as soon as you can. You don't want to make it mount up. And also, we do understand that actually working from home is different to working in a classroom. Some of you might actually prefer it, but for quite a lot of you, it's not as good as having a teacher right there at the time. And I do totally understand that. Just a couple of points. Your lab books, this is a perfect opportunity to make sure that everything is up to date in your lab books. You have all of the information. If you can get them all written up and all the questions answered, it will make things easier going further down the line. At the moment, we're dealing with the second year's lab books, so it's really important that you are doing what you need to do to stay caught up. Also, please make sure you keep an eye on Teams. The classes that you're in, we're putting work directly onto Teams so that you're able to get the work and get things completed and get the best mark possible. Let's be honest, what this is about, being at college, is to get you through to the next stage, be that work, be that university, be that an apprenticeship, which is sort of somewhere in between the two. But it's really important you stay engaged, stay focused, because they will be examining you next year and you want to do as well as possible. If you want to, just as a starter, always worth having a quick look at the starter. Name of the mechanism for propane and chlorine. Remember, propane is an alkane and chlorine is a gas. Remember, there's no double bonds, but there probably is a little bit of light. And this will give you a clue as to what we're doing today. So, it's really important that you know your functional groups. Now, this is a picture of some functional group interconversions, and this is the aim of what we're going to be doing by the end of here. It won't have as many in there because you're not required to know all of those yet. Some of them are second year ones, but this is what you're looking for at the end of the day, something a little bit like this. So what we're going to be talking about is synthetic roots. And what synthetic roots are is how we actually make chemicals. We start off with a chemical, we make another chemical. Things like drugs that you may take for illnesses, so the antivirals and things like that people are experimenting with to see if they can get an effect on the coronavirus, for example, or something like an antibiotic, for example, penicillin. These are things that actually, penicillin, for example, was initially extracted from a fungus, but actually then they managed to create the molecule synthetically. They made it from another molecule. And synthetic roots is where you start getting into learning how to make these compounds. It's actually what organic chemistry is all about. We sort of go through what we're sort of like talking about, excuse me. We go through what all these chemicals are, what they do, but actually really what we want to use it for is to make new compounds. And in fact, lots and lots of money at the moment is being spent making these new compounds. So what we're hoping is that first you'll be able to identify functional groups in molecules, and from knowing the functional groups, know how they may react. And then you're going to have to start putting reactions together to make target compounds. So let's have a look at this. We have two molecules. These are quite big molecules. This looks like a steroid of some sort because it's got the 6-6-6-5 ring configuration. I'm not entirely sure what it is. Someone might be able to tell me what it is, but it looks like a natural molecule of some sort. But it has certain functional groups. And we can see we have a functional group here, we have a functional group here, and we have a functional group here. The rest of it is just carbons and hydrogens. So if we were to look at what this functional group is here, what do you think it is? We have a carbonyl, so C double bond O, it's in the middle of a chain. So if you think it's a ketone, you would be absolutely right. If you think it's an aldehyde, yes, I can see what you mean, but aldehydes, remember, are at ends of chains, so they'll have a hydrogen next to them. More functionality, we have this here. We have a carbon double bond carbon. So what type of functional group is that? If you said an alkene, you would be absolutely right. We have carbon double bond carbon. It's an alkene. It means that actually this part of the molecule is now unsaturated. Can you think of any reactions that might take place on the carbon-carbon double bond? Well, we might think about bromine reacting with it or hydrogen bromide reacting with it, depending on what we're trying to make. What's this one here? You'll notice this has a wedge on it, and this one has a dashed line on it. I'm hoping you remember your shapes of molecules, what these mean. Don't worry about this notation at the moment as to what it means. I can tell you what it does mean, though, is that this carbon is called a chiral carbon. It's a chiral center, and it means that actually, if this was pointing in the other direction, this would be a totally different molecule. But this particular functionality here, what is it? It's an OH group. It would be an alcohol group. Could be hydroxy if you were trying to name this beast of a molecule, but I've got to be honest with you, I wouldn't even try naming this systematically. We'd just find out what it is, and it's probably got a name like Bob or something like that. What about this one here? We have exactly the same thing here. We have an alkene, and in fact we've got an alkene, 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 alkene. You'll notice that I've got carbon double bond carbons here, but actually I'm not suddenly going alkene. Do any of you know what this particular six-membered ring with carbon double bond carbons has a very special name, and that is a benzene ring. We also have here our carbon double bond oxygen and an OH. So this is on the end of a chain. However, it's not got a hydrogen on there. So what is this functional group? It's definitely not an aldehyde. It is what you would get if you oxidize an aldehyde, and that is a carboxylic acid. So being able to look at an organic molecule and go, okay, this is this, this is this, this is this, is a really important skill, because if you can understand what functional groups are on there, you can then use that molecule to make other molecules. Or if you understand which functional groups are on there, you can also think, this is how I put this functional group on, this is how I put this functional group on, and you can work up a synthetic route from one chemical to another chemical. So having a look at these, with reactions that you've gone through so far, we know that alkenes undergo electrophilic substitution reactions. If we look at this one here, alcohols, they can be oxidized, They can be substituted with a bromine or a chlorine or something like that. So there's lots and lots of things that we can do with this. If we have a look at this carboxylic acid is acidic. Now, if we think about it, which one of these is probably going to be most soluble? And I would say it's going to be the carboxylic acid, because we can lose this hydrogen. We then have something that looks a bit like water. This is probably soluble as well because it's got an OH group and it's got this functionality here where we have a C double bond O, which is delta negative. This is going to be delta positive. So this is probably likely to be soluble in water as well. So what I'd like to do, pause the video while you do it. Try and work out what would happen. What is the radical substitution mechanism? You don't need to do curly arrows, but you do need to come up with a sort of mechanism for reacting propane and chlorine. So pause the video while you work that one out. Last chance to pause it because I'm moving forward. So if you are a bit confused, remember UV initiation starts it off, so that is when the radicals are formed. Propagation is when you have one radical at least and it reacts with something and makes another radical. A termination is when two radicals combine and you no longer have a radical. But next thing I will do is show you this reaction mechanism. If you need to pause it to have a proper go, please do so now. Okay, so this is the answer. We have our initiation step where we have chlorine, chlorine. One electron, if I draw chlorine, chlorine, and here we go again, my terrible penmanship on here. If we have one electron going in this direction, one electron going in this direction, we will see if the bond is made from two, oh, it's all gone wrong again. If it's made from two electrons, one electron goes one way, one electron goes the other way, we have a homolytic fission. So they are both the same. There's a fission because they split up. Then what happens is the chlorine reacts with some propane, and what it does is it abstracts a hydrogen. A hydrogen comes off. And what then happens is another chlorine will come in and react with that, and it will regenerate the chlorine radical. So we have a propagation. The reason why we have propagation is because we have one radical species and a radical species is generated. Here we have a radical species is generated. Termination is, as it says, the end of the reaction. We have two chlorine radicals here. They react together, or we have a chlorine radical and a propyl radical reacting together. Or we have two propyl radicals making some hexane. So let's have a look at electrophilic addition. We've done electrophilic addition before, so what I want you to do is to work through and think, oh, and I've just put it up on there. I thought there was going to be a little clue. Ignore that for a second. What I want you to do is to write out the mechanism between ethene and chlorine. If you need to pause it, please do so now. I'm going to move forward so we can see it. So we can see here that the carbon-carbon double bond, which has an excess of electrons, it has lots of electrons in there because it has your sigma electron, your sigma bond, and you have your pi bonds which sit on top of there. They are going to react with one of the chlorines. Because the chlorine has instantaneous and induced dipole moments, it will have a delta positive, delta negative. So one of them just becomes slightly more positive because some of the electrons have gone in this direction. It could be because their neighbouring molecule has done the same, or it just could be one of those things that happens. What will then happen is the chlorine bonds onto here. We have a carbocation, and the carbocation reacts with the chlorine ion, or the chloride ion here, which then bonds into here. You'll notice the difference between this and the last mechanism that we saw is we do not have homolytic fission. This is heterolytic fission. because we end up having something that's positive and something that's having negative. So both electrons from that bond are going in this direction. And we end up making 1,2-dichloromethane. We also have haloalkanes and nucleophilic substitution. This is something that you guys should have seen before. It's when we're talking about haloalkanes. So what I would like to do is to see if you could have a look and remember the mechanism for this one. It is really important because these are mechanisms that you might have to reproduce in the exam. So pause and have a go at it, and then I'll reveal the answer in a few seconds. There we are, there's the answer. Now, the big difference between this mechanism and the mechanism before, so if I go back to the mechanism before, we can see we have an intermediate formed here. So this would be an intermediate because it's got a carbocation. The reason why we can have that is because carbon only has 3 bonds. So we can have something with carbon with 3 bonds. It's not particularly stable, but it does exist. Whereas in this case, carbon has 4 bonds. If I added the OH to it and we made an intermediate, we would then have carbon having 5 bonds. That is definitely not stable. What happens is the OH minus comes in here. It starts making a bond with the carbon. As it's making the bond with the carbon-chlorine bond starts getting longer and longer and longer, and eventually the chlorine goes. So this is a one-step process. We have a heterolytic fusion and a heterolytic fission in this case. And of course, because this is electron rich, because it's an electron paired donor, this can be seen to be a nucleophile. Because this is happening and we're not changing the number of bonds on the carbon, this is a nucleophilic substitution reaction. So, what we need to understand is how certain chemicals are made. We need to be able to identify those functional groups, and we need to know how to make it. So if you have a look in your textbook at page 240 to 241, you should be able to see some examples of this. Now, your task for today is to get some paper or do it on a computer. That thing right at the beginning of the PowerPoint, I want you to make a sort of mini version of that. So if you have a look at page 17, start with propene, draw all the things you can make with it in each step, and include mechanisms where you can, because it will help you learn them. And you need to see all of the things that you can make with propene. If you think about it, if you add steam and a catalyst to propene, an acid catalyst I believe, you make propanol. So what can you make from propanol? Can you make it go backwards and things like that? That is what you're going to be required to do. Have a look at that first slide again, or download it from Moodle. Have a look on page 17. Oh, my son is just about to appear. You right, Alfie? There we are. You just want to see what I was doing. Have a look and see what you can work out. So that is going to be your work for today. I'm missing you guys. I really hope this lockdown thing is over soon so that we can get back to the business of getting you through your A-levels and getting you off to university or to your dream job. Hope to speak to you all soon. Have a nice one. I'll just make the camera big. See you later. Oh, there we are. Alfie wants to come back in. Say hello.
Bye.
Bye. There we are. He likes Minecraft. Yeah. I told you all those Minecraft videos aren't my fault. They are my son using YouTube. That's what happens, isn't it? You use my YouTube, don't you? Yeah. I've not paid him to say that at all. Yeah, definitely. Anyway, have a good day. Bye-bye.